And I just want to quickly mention that this talk is done in collaboration with my colleagues, some of them at Intel and some of them at UC Berkeley. And I myself is on a joint appointment at UC Berkeley and at Research Institutes of Sweden. And so without further ado, let's get into the talk. And let me first start with some high-level inspiration and motivation for this study. And so I think we all would agree that when it comes to neuromorphic engineering, it's an exciting area, but at the same time, programming neuromorphic hardware, that can be a challenging process sometimes. And of course, algorithmic development is not straightforward. And so one line of work these days is to think, okay, how to streamline this process. And in that way, at our group, we are often think and we're getting an inspiration from Mars levels for information processing devices. I'm pretty sure most of you are familiar with that idea, where we have 3 levels, and at the highest level, which is a computational level, we will essentially have our applications, so the functionality which we would like to achieve. Then in the middle, we have an algorithmic level that connects the whole hierarchy. And at the algorithmic level, we'll talk about such things as data structures and how we do the control logics and things like that. So this is the level of our programming abstractions essentially. And then we have the lowest level, which is also very important, right? That's an implementation level. This is where our computing hardware resides. And so our focus today would be primarily in this middle algorithmic level, where we believe that hyperdimensional computing, or as we also call them, vector symbolic architectures, which is a framework for distributed computing, we believe that this might be a very important component for abstracting and making the development of neuromorphic algorithms simpler. And so, yeah, so we believe that this can be a great abstraction for programming neuromorphic hardware. And importantly, as Chris was given in the previous talk, on top of VSA, we think that vector function architecture, that is essentially an enhanced version of VSA, will play an essential role. And so when it comes to vector function architecture, let's just repeat a few key points we need for this talk. But in general, Chris has already done a great job introducing VFA, so I just will lightly touch on that. So first of all, right, so what we need to do to form VFA, we need to have a random base vector that we denote as Z during this talk. And the simplest case would be just to form and draw phasors uniformly. And as an outcome, we will get sync kernel that will characterize the similarity between different scalar values that are represented with this VFA. And so what's important now is that we can take a couple of VFA representations and for different scalars, let's say X and Y, and we can bind them together, whereas the binding will be just a Hadamard product, and it's depicted here. So which essentially it's rotating the corresponding components of the vectors corresponding to X and Y. And so what's important is that in VFA, there is a meaningful interpretation in the original space so that the result of binding going to correspond to the addition of the original scalar values. And we're gonna leverage this property. And of course, another operation that we can do is going to be the superposition of these two vectors together. And superposition will be just component-wise addition of the phasors. And then we often would normalize, since once we do the component-wise superposition, so we don't have phasors anymore, so we often would actually normalize the magnitude of each component. So we are back, we project back to the unit circle. And so with that, Chris already has presented a number of applications of VFA, but So of course, the natural questions, what are the other examples of VFA? And so today we're going to focus on one particular example, that is integer factorization. And I will mostly use semiprimes factorization, where we have semiprime S that is just a product of two primes X and Y. And so of course we know S, but we have no idea what is X and Y, and we would like to know it. And that's a very well-known problem, partially because it plays a key role in various encryptions. Of course, what we saw on the previous slide is that we have this beautiful property of VFA that the binary operation corresponds to the addition in the original space. And this is not exactly what we need in order to work with factorization problems, right? Because for factorization, we would like to have some correspondence between binding operation in VFA space and multiplication on the original values. And so here, like a very simple trick is, and probably everyone would immediately recognize that, so we can just rely on log transformation. So once we do the log transformations of our scalar values, so then once we form their corresponding VFA representations, so now all of a sudden, due to that property that addition in log domain is actually multiplication in the scalar domain, so now we have link between the binding operation and multiplication in the scalar domain. And we're going to rely on this log transformation. And so now we essentially see now this integer factorization as some kind of stress test for VFA, right? Because VFA, as we position it, is a neuro-inspired way to work with numbers. And of course, in some sense, it's a brain-inspired way. And yeah, brains are probably not that great at integer factorization, but now since we have this way to work with numbers, so why don't we try it? And so we have now a way to represent our problem in VFA terms. But we still need to solve this factorization aspect. We still need to solve the factorization problem. And these kind of problems that are now looked as vector factorization problems, they are common in DSA. And that would be a typical form of a factorization problem. And there is a recent proposal for solution on how to approach these kind of problems without going into the brute force search. And that's called a Resonator network, and it's in its essence, it's a recurrent neural network that solves the factorization problem iteratively. It can also be seen as a combination of several Hopfield-like content addressable memories, and it uses that idea that binding operation is invertible. And the main strategy that Resonator network is using is search in superposition. And so here is the circuit of the Resonator network that is set to solve this particular vector factorization problem. And so in essence, what we try to do, we try to simultaneously form predictions of each factors, so A, B, and C, that we have in our problem. And so we try, like, for example, for factor A, we try to invert the current predictions of two other factors, and then we assume that we know the code book of our vectors, and it's assumed that the correct factor is available in that code book. And so by inverting the binding, we are getting the current prediction of factor A, and we project it back to the codebook space, and that provides us essentially weights, like how likely each of the items available in the codebook corresponds to that correct factor. And then we can again form, a weighted superposition vector now, which is where essentially all factors reside simultaneously in our vector. And we can just repeat this process. And eventually, we will converge to the correct solutions. And so now let's just, again, so now we've essentially seen all the components we need to do integer factorization. Let's just recapitulate what we need to do, what would be exactly the flow of solving the problem. So first, we just need to define our set of primes P of S. And that should include all the primes that are potential factors of our semi-prime S. Then we need to populate the code book, or we also would call it item memory. And for that, we would generate the base vector for VFA, and then we would form a VFA representation for every prime in our set P of S. Then the last step would be to set up the Resonator network to factorize the VFA representation of our semi-prime S. And this is how, like these are just two different ways to demonstrate the Resonator network. So on the right, this is just a circuit for doing prime factorization. And it's, as you can see, it's kind of very similar to the circuit, to the abstract circuit that we've seen on the previous slide, with few exceptions. That, for example, here, the nonlinearity that we will use we're going to use this normalization to unit circle. And this is just a mathematical formulation of the Resonator, of the dynamics of the Resonator network. And so, just not to be too much abstract, and to highlight one important thing that is happening in the Resonator network, we have to keep in mind that the predictions that we are forming for the factors of the semi-prime, this essentially superpositions of entries of our codebook file. And so it's important to think about the way how VFA representations, how do they exist in the superposition? How do they behave in superposition? And to understand that, let's consider an example of storing a set of 4' of log transformations of 4' in a single superposition vector. So essentially, S now is a single VFA representations where these 4 elements of the set, they live essentially simultaneous in that vector. And so what we can do some kind of decoding. Like, let's try to read out what is inside this superposition vector S, and we can do that by measuring cosine similarity between S and VFA representations of various scalar values. And here on this plot, blue lines, they correspond to the locations of the actual elements of the set. And so what we can see here is that, so what we read out from the superposition vector is some kind of strange weighted average, so to say. And so an interesting question to ask is that, is it the only way how it can be, or is there anything that affects the way the superposition vector behaves? And indeed there is. So what is there is that when doing the VFA representations, one can explicitly state that there is a kernel bandwidth parameter beta. And on the previous slide, we haven't explicitly taken into account beta, so therefore one could say that beta was set to 1, but we can actually control this parameter. And in fact, what happens is that this parameter affects the way the superposition vector behaves. And so let's see some animation. So what we start to see here is that, and what's happening here is that we plot this readout from the superposition vector for different values of beta. And so what we see when beta is small, we have this thin red line here, and that corresponds to the actual mean of the elements of the set. And that's what we see, that when beta is small, we're essentially in a kind of sub-symbolic mode where the superposition vectors essentially performs the mean operation on our VFA representations. But once we start increasing better, beta, we start to see that interesting behavior emerges. So now at this stage, when beta is 2, we have actually 2 bumps here. So we actually start to see that one of the elements of the set, the one that is furthest away, it starts to form its own bump of activity. And as we continue increasing beta, so we start now to see like 3 bumps, and finally, for large values of betas, we start to see that that now different elements of the set, they are individually decodable from the superposition vector. And that can be seen as another extreme of the superposition vector, which is like symbolic mode. So we are now in a symbolic mode. And this is exactly the mode we need to use in order to do integer factorization, because every entry of the code book for integer factorization is like a unique symbol. So this is the mode we would like to operate at. But sub-symbolic mode can be useful for other problems. And so with that peculiarity of a superposition vector, let's see how the resonator network would behave and how would it solve the problem. So let's just consider some simple semiprime. So this is our semiprime. We know the correct factors, and let's define the set of primes. And for the sake of this example, I will only choose 10 primes. This is just purely for the sake of visualization. So it's a small set of 10 primes. So we choose our parameter beta and dimensionality of vectors that is denoted as n. We create the base vector z. We populate the code book, and we form the VFA representation of our semiprime, and we are ready to set up the resonator network. And so let's see in action how the resonator network would act. And so what we see here is that on the y-axis, we see the iterations of the resonator network on the left for factor number 1, and on the right for factor number 2. And color map, it shows the similarity between the prediction at the current iterations and all 10 entries of our code book. And so these rectangles in each row, they show the winner. They show the entry of the code book with the highest similarity at the current iteration. And what we see that at the beginning, it's very chaotic. Things jump around, and that means that resonator network is sort of exploring the space. It's trying to find good factors. So it hasn't yet converged to a concrete solution, and sort of many solutions, they compete simultaneously. But so we soon start to see, and like here, for example, so we start to see that it looks like it's honing in on one particular solution, and as dynamics of the resonator network evolves, eventually it finds the correct factors, and it just stays there. So it converges to a particular solution, and it's done. So the factorization process is complete. So that's exactly that's the way how the resonator network behaves. So it's a bit chaotic at the beginning, and then once it starts finding the solution, it will eventually converge to it. And so now, of course, the next question is, all right, how would that behave when we start, scaling the problems, and how the different parameters of the approach would affect the results. And so what we see here is that on this figure, we see how the accuracy of factorization. So we just run, number of random factorization problems and computed the average. How would it evolve depending on the dimensionality of our VFA representations against the size of the code book? And what we see here is that obviously for larger vectors, we are capable of factorizing problems of larger size, because the search space of the problem, it is defined. It grows as squared size of the code book. And so another important observation here is that number of iterations of the Resonator network is indicative of the factorization performance, meaning that when we are in a high fidelity mode, the accuracy is very high. We need only very few iterations to converge. And then once the Resonator network starts to need too many iterations, it also means that the factorization accuracy is going to decrease. Another sort of scaling experiment was to see what would be the required dimensionality of VFA representations for a given size of the code book, such that the accuracy of factorization would at least be 95%. And so what we find here is that while the search space grows quadratically with the size of the code book, the required dimensionality, it scales just linearly. And another important thing is that the required dimensionality, it only depends on the size of the search space, but not on the range of the prime numbers themselves. So that the size of the search space is what really defines the required dimensionality. And of course, another natural question would be whether the approach is only applicable to semiprimes or whether it's more general. And so the answer to that is that it can be extended to any k almost primes by essentially just adding an extra factor to the dynamics of the Resonator network. So in this case, we can just add one more factor, and we see that once we do the simulations, qualitatively, it behaves the same as the case of the semiprimes. And with this comes my last slide. That is just a summary of my talk. And I started with this idea of Mars levels of hierarchy, and essentially we can see that the whole talk was trying to show a particular use case, just starting with the integer factorization at the computational level, using HDC, VSA and VFA at the algorithmic level, and at the computing hardware to this end, we just implemented it on the GPU. And so in general, so our message to the community would be that VFA and VSA, they can be used as an abstraction level to do solutions to various problems. And in this particular example, we focused on vector factorization, and we connected it to classic computer science factorization problems. And we believe that it's a promising way to approach a broad class of various factorization problems that can be now seamlessly distributed using the idea of VFA, and therefore can be implemented on parallel hardware. And this ends my talk, and I'm glad to answer to any questions.